Yeah, thanks, Dima, for inviting me, and Andrew for organizing that. Yeah, I think I'm quite lucky to be the first one to talk. I thought there would be half this many people by this time in the morning, but anyway, yeah, glad to be here. So, yes, my name is Teo de Campos, or well, people call me Teo as well, I don't mind. As she said, I'm currently at the University of Brasilia, which, well, is in the capital of Brazil, right in the, well, more or less in the middle of the country. But the work I'm going to talk about was developed at the University of Surrey, and well, at the moment I'm actually there as a research visitor just for, well, a month. And this was actually, well, mostly done by my PhD, well, she was a PhD student back then, Nazli Faraj Davar, with some help from Joseph Kittler. Yeah, it was interesting that Dima, when she introduced, she said, well, we're going to have the invited speakers, and then we have talks about state-of-the-art work, which actually makes sense for me, because I think this works as a maybe sort of introductory talk. That's probably one of the reasons I'm the first here. I wouldn't say the work I'll present here is actually, well, is not really state-of-the-art anymore, but I think it works as a basis for next steps. So it was mostly, most of the results were actually obtained about, well, around 2 years ago, actually. But well, there are some interesting sites there. The talk, well, the title that was assigned to my talk, well, like I said, is Transductive Transfer Learning for Activity Recognition. There was this activity recognition bit there. So I thought I would start the talk by focusing a bit on the application to, well, action and activity recognition, which is actually what motivated me in this work. And then I'll talk about transfer learning and the techniques that we developed, and show results and discuss next steps. Right. So just to give some background, I realize PBFPC doesn't work with clicks like this. So I'll try this one. So this work was actually motivated by, oops, wrong screen. Sorry. Yeah. So this was motivated by a project, an EPSRC project, which was called, well, ACASBA, Adaptive Cognition for Automated Sports Video Annotation. So essentially, the idea was that, well, if humans can sort of learn the rules of a sport by just watching TV or watching people playing it, why can't computers do that? So maybe we should try and get computers to do it. So we have a system that incorporates lots of, well, bits of, well, basic computer vision techniques for things like, tracking curved lines, detecting and tracking players, and actually more difficult, tracking the ball, tennis ball, which is quite small and difficult just even seeing these, low resolution videos. And the idea is that, well, if we have all these primitives, and we can track the ball and project onto the sort of a rectified view of the curve, and we can, using a motion model of the ball, we can actually detect when relevant events happen. And so if we know where those events happen, and if we know where the players are and what they are doing, we should be able to infer rules, in principle. So that turned out to be quite a challenge. So I'll get back to this. So what we ended up focusing on was actually on, well, basically starting from a model of the rules, sort of a broad model of the rules, and then the idea was to use lots of observations of video sequences of a sport, and then trying to learn more parameters of this model. So we tried several things, and one of them was coming up with this finite state machine that describes the key events in tennis games in a way that's quite generic, and the ball coordinates in the court, they are quite generalizable. And basically there's, well, 2 blocks here, one for each side of the court, and transitions between them. So given this model, the task becomes actually, learning weights for the transitions from one state to the other. So if you give a tennis game, we learn a set of weights, and the idea is that, well, given that we have this model, can we then get this to work on a slightly different modality? For instance, if we start from singles games, can we then adapt for doubles, which sounds quite trivial, but not only we have more players, but also the ball can bounce on a larger area in doubles, or the ball could bounce around here, and that's allowed. So, and that's something you can only observe using a long time sequence, and then you start populating weights in a different way. So essentially, yeah, this is just all to say that, well, if you have some prior knowledge of a domain, adapting to another becomes a lot easier. So this piece of work here, which was actually led by David Rindrich, it focused on the high level sort of activity recognition, like modeling the whole space of allowed actions in a video sequence. And like I said, there are several components to this system, and the focus of my work is actually on observing the players and classifying their actions. So we built data sets like these ones. So for each tennis match was a data set. So here, 2 sample data sets. We actually built several of them. And one thing you can see, so the data set was essentially built by using a very simple person tracker and the ball events to locate things in time. So essentially, whenever the ball changed motion suddenly, we grabbed a bounding box around the players and extracted a small video sequence. And so in a game of doubles, you get a data set like this one, and you can see that the number of serves is much smaller than the number of non-hit actions, which, this includes running or waiting for the ball or any other action that players do when they're not actually interacting with the ball. So it's a very unbalanced data set, and it's quite challenging. And it's interesting because it's not about activity categorization, so everyone knows that this is a card game, but it's more specific, it's detecting the specific action of a player in a game. And yeah, so there are other card sports. So one thing I didn't mention when I showed that diagram is that same general model of rules also apply to badminton, and it should work as well for table tennis. Maybe not for volleyball, but if you stretch a bit, perhaps it might be possible. But anyway, we processed badminton games as well with the same sort of pipeline, getting samples like this. But as you can already think, this is a quite different domain compared to the original game. And also, even back to tennis, even though these are 2 matches of tennis, just the fact that they are in different places means the low-level features will be slightly different. The fact they are wearing, actually these 2 players are playing against each other, they are the Williams sisters. But there are different players on the other side, so their low-level features are actually quite different if you just blindly extract features. And even the coding system, so that's PAL and this one is NTSC. So all these little things that they look trivial to us, but when you think of low-level features, they are actually they actually populate different spaces of the feature space, and so you get different marginal distribution. And going from tennis to badminton becomes even more complicated because there is no way you can map this action, the serve action in tennis, to a serve action in badminton unless you actually, use an articulated body tracking model and maybe a lot of prior knowledge, because otherwise this looks a lot like the normal hit in tennis, except that they have both hands near their racket. But if we focus on the other actions, we can actually transfer between them. Right, so like I said, we have a mechanism to, well, track players, which is, well, basically if you track the curve and do background subtraction, it's quite trivial. And we have quite a good ball tracker which locates things in time, which actually facilitates things. So basically, if you know when and where the actions happen, it becomes a lot easier to tell what is the action, right? So yeah, so if you see this as, well, this is a space-time block, right, of the whole video sequence, and you can tell, like, this illustrates where relevant actions happen and where players are in space and time. So if you just extract these little sub-blocks, you don't need, expensive or sophisticated feature extraction methods that use a pool of local descriptors like a bag of words or Fisher kernels, or even like a global CNN would probably not do a great job here either. This actually works better if you just look at these local regions and extract a single descriptor, a single space-time descriptor. We show that actually this gives better results than things like bag of words. And not only because if the action is well localized, you don't need such a generic feature space, but also because if you look at a descriptor like the Hog3D, that's the one we used by Alex Glazer and others from INRIA, or I mean there are lots of other Huff transform based descriptors, including SIFT or SIFT3D, or lots of other space-time descriptors. Essentially, they're all about splitting the space-time block into sub-blocks and then extracting some sort of local descriptor, like actually this is the lower level, like a gradient, projecting, computing local gradients and basically pulling them into, well, in this case, just summing, adding up those local descriptors into a bigger descriptor, right? So essentially, if you look at this, there is already a pooling operation happening here, which makes it a bit invariant. And so a Hog descriptor can actually be seen as a small spatial pyramid kernel, right? So it becomes, in this sense, when the action is well located, it makes no sense to add another layer of pooling on top of that. Pooling of descriptors which are already made of pooling. So you don't gain that much from that. You actually increase the invariance, but without gaining discrimination power. Right. So anyway, so this is just to motivate, but well, and giving a bit of details about the feature extraction. So we also, further to work on these action data set, players' action data sets, and a number of other traditional action classification data sets that were available back then from UCF and well, there are a few others. When we started focusing on transfer learning, we saw that actually no one, at least back then, no one was doing transfer learning for action classification. This was more than a couple of years ago. And people are using data sets like these ones. Well, the most widely used for basic pattern classification or machine learning problems was these digits data sets, USPS and MNIST. So they're essentially, well, handwritten digits extracted in slightly different ways or from different sources, so they actually constitute different domains. But the number of labels is the same on both of them. It's just the marginal distribution of the data changes. So you can, in those data sets, you can just vectorize the raw pixels, and that's what people normally use as the input vector. There is this COIL 20 data set, which is actually it's from Cornell. It's a data set of 20 different objects, very simple objects that were photographed in a turning table. So you have 20 classes, and the different, each quartile of angle orientation of these objects is taken as a different domain. And then there is this face, pi dataset, which is a face recognition dataset, a small one, but it's quite simple. Faces are nicely centered and so on. But the illumination changes a lot, so different illuminations are taken as different domains. Or you can actually use it as a different, in a different way. You can say that different people are different domains, but the system is trained to classify light orientations. But normally you deal with it as a face recognition problem. And actually the most popular one for earlier works on transfer learning was this set here, which is essentially the Caltech and Office data set. So essentially they picked up a number of classes of objects that you find, they're commonly found in office environments like computer screens. And so acquired them using, basically searching Amazon for images of those objects, getting images from webcams, or higher quality images with DSLR cameras, and also they extracted the same set of classes from Caltech. So essentially each acquisition method is treated as a different domain. And so in these data sets here, usually people are just using raw pixels or maybe pixels with PCA applied on them to do the feature extraction. But for these ones, the standard method for feature extraction used to be essentially bag of surf descriptors, which, I guess I don't need to give details about that, but this was a very commonly used. You extract local surf descriptor and apply a pooling of those features to generate a vector, which is essentially a histogram of those descriptors. I can come back if people ask questions. But more recently, the decaf features became a standard for a little while they were standard for anything in computer vision. So they are essentially the activation extracted from the 6th layer of the AlexNet. Just before the higher level layers, what they show in the decaf paper is that this layer encodes a lot of information about the data that's relevant, but is not specific to a classification domain. So when they realized that this layer was better than the other ones, they thought, so these layers encode information in a way that's generalizable. So they actually claim that you shouldn't need to do any domain adaptation if you use these features. And we actually show that if you do domain adaptation on those features, you still get an improvement. And I guess now is well known. Right, so now into actual transfer learning. Some of you guys may have seen these. It might be quite basic, but essentially, in traditional learning, if for each different domain you train a different learning system and just focus on that data set, which is just like Dino was saying. But with transfer learning, instead of doing that, you can acquire some knowledge from the source domain, and then instead of learning the new domain from scratch, you can just update the learning system using that knowledge, right? So that way, this target data set can be smaller, so you can, because the learning system doesn't start from scratch. In a way, when you do fine-tuning to a different domain, you're essentially doing the same with CNN. You have the same sort of advantages. But there's a whole range of methods to do that. So the idea is that, because with transfer learning, you start with some background knowledge, you have a higher start in terms of performance and also a higher slope. And you can expect to have a higher asymptote on training as you iterate or as you give more data. Because since you started with knowledge from a different domain, your system is inherently generalizable, right? Because it's already a generalization. So it becomes more robust to different data. So I'm showing here this diagram from Pan and Young, which is a taxonomy of transfer learning methods as it was back, I don't know, like 4 years ago, roughly, well, maybe 3 years ago, roughly. Not everyone agrees with this taxonomy. And in fact, different communities give different names to things. So from this taxonomy, essentially when you have information in the source domain, but you don't have so much information, or you don't have labels in the target domain, they call this transductive transfer learning, which is, well, the title I chose to use, well, as highlighted here. Well, I realize this is harder to read, but, and yeah, it's specific. When you have you know, different domains but single tasks, so the classification target is the same, but you have different, you know, Markov distributions. They would call it domain adaptation. So domain adaptation here is a subset of transductive transfer learning according to that taxonomy. But more recently, people started calling lots of things domain adaptation, and including some people say transfer learning is a subset of domain adaptation, and actually what comes into this category is what they call unsupervised domain adaptation. Yeah, but anyway, I'm just showing here for illustration. We can debate this later. Right, so now into the method we actually proposed. Basically, we came up with this pipeline, and the problem we're focusing on is this. Essentially, you have as input a source domain, which is a set of feature vectors and their associated labels. And you also have as input data from the target domain, but you don't have it, their labels. And the task is essentially to infer the labels for the target domain. So essentially, like classify the target domain samples, given that you have knowledge from source. Right? And so, okay, in the first step of this pipeline, essentially we apply a global transformation using a method that's, well, it's basically a shared space detection based on maximum mean discrepancy minimization. So I'm gonna focus on this method now. I guess I don't have the time to give much detail, but essentially the idea is that you combine all the source and target samples into a big data matrix, and the idea is to find a linear projection of this space that maximizes the data variance, which is essentially what PCA does. But at the same time, we want this projection to minimize the difference between the means of the two domains, right? So we want to minimize the maximum mean discrepancy. So a way to do this, this shows how to express that into matrix algebra, and a way to solve that is essentially by using a generalized eigenvalue decomposition, right? So, yeah, so essentially this matrix here encodes the maximum mean discrepancy, and this one is just a normalizer of the data. But so you try to find orthogonal vectors that are, you know, when you multiply them to with this data set, projected data matrix, you get it to become equal to this eigenvalues matrix here times that matrix, right? So, you actually solve quite easily with eigen decomposition method. So this is just, well, it's a little illustration in 3D. Essentially, let's say you have data like that of two domains. You essentially magically project it into a lower dimensional space where the means of the two domains, they fall quite close to each other. Right, so the next step of this pipeline is, so this first step was a global linear transformation. The next step is a local transformation, which depends on the data. On each sample, actually. So essentially, for each sample, we want to find a transformation that's basically, you know, a vector that shifts it. This is a very simple way to model very complex transformations. So if the transformation is a local translation, you essentially can do any nonlinear transformation if you look at it from the global level. So I'm not going to go through the details, but essentially what we want is, we model the target domain samples using a GMM, and what we want is essentially to find this translation that maximizes this distribution of the, the probability that this data after this transformation belongs to that GMM. So yeah, similar to the target ones. I can come back to this if people are interested, but what we come up with is basically a gradient vector that is computed. Well, it's basically a gradient with respect to the with respect to x for all the parameters of a GMM, right? So if next slide illustrates this. Basically, if my target samples are modeled with this GMM, and this is a source sample, so you essentially calculate the gradient with respect to each component of this GMM, and as with normal, as you do with gradients, you sum them up, so you end up with that. So those arrows should be pointing the other way around, actually, but yeah. So by combining those gradients, you get one gradient vector that essentially brings this sample somewhere where this likelihood increases. Right? Right. So I can show you some examples of this later with results. But the last step of this pipeline is a supervised, sort of semi-supervised step. So up to here was all unsupervised in the sense that we were just trying to make the two distributions more similar. And in this point, we actually use classification results using the model trained only on the source domain in order to work out how to modify the data to adapt to this. So we propose two different ways of doing that. Essentially, the first one, which is quite simple, is basically about shifting the expected value of samples for each class so that source and target become more similar. This is, in a very high level way, this is essentially achieved by using the ratio between the expected value of each class in the target domain, which is something you compute by using classification results, over the actual average, the actual mean values for each class in the source domain, which you compute quite trivially because you actually have the labels in the source domain. And this is, I'm basically showing how to compute the mean, essentially the expected value for each class in the target domain. This is essentially a mean, an average computation, but using posterior probabilities. So this is done for each class. So another transformation we proposed is a bit more complex. Instead of just reweighting features, we essentially, we not only reweight them, but we also translate them. Right? So this transformation is applied sort of semi-globally, so it's globally for each class, right? So it's one transformation for each class applied to each feature, to each element of the feature vector, right? So just to avoid overshooting, we use a weighting factor here. So the transformed vector is weighted sum between the original position and this transformed feature vector, because this transformation depends on the classification results with the original model. So because the original model is in a different domain, it might make mistakes. So you can't really fully trust it. Right, so, okay. Right, so I gave all the core techniques, but I guess I ran out of time. I'm about to run out of time. So I'm just going to quickly go through results. So basically, we did, told about this weight vector factor there, and so we did some tests, with different values for it, and we found that this is actually data set dependent, but just using theta equals 0.5 works quite well. So here's some in general, right? So here's like I'm showing the 3 steps of the pipeline in one sample data set. So source and target are shown as circles and pluses. So after this is actually after the first step, which is the matching the means. After the second step, you do this local transformation, which you can tell is not linear. Well, you have to spend a bit of time looking into this. And then the last step, which is a supervised one, actually brings classes of the same label closer together. So you get better results. Right, so in the final step, which I'm actually going to skip, we proposed a way to compare data sets and work out, measure the difference between domains so that we could use those measures to automatically tune classifier parameters. So I'm not going to talk about that now. We can discuss that in the breaks, I guess. But essentially, well, I got some benchmark results on a number of data sets here with all those domains that I was talking about in the beginning. Here are some more or less recent methods published on those data sets. And these are different variations of our system, using different parts of it. And this is the one that actually combines all the steps. And basically, we were state of the art when we proposed this. And this is using decaf feature. You can tell that there's actually quite a significant improvement that we get with our pipeline comparing to just using a simple classifier on decaf directly. So there's quite a good jump there, which means you can still gain quite a lot by doing transfer learning on CNN features. So this slide is just summarizing my talk, which I guess I don't need to do now. But one thing about that's interesting, maybe it probably leads to the next talks, is that, well, what we will do later, right? So essentially you can see this, the pipeline we proposed as a chain of transformations, right? Which is essentially what you do with a CNN, except, so it's not so trivial to map what we did through a CNN because if you have one convolution kernel, you apply the same transformation to the whole data set. But what we propose is to, in 2 steps they're different. So one of the steps, the transformation is actually a function of the data sample itself. And so the parameters of the transformations are samples and depend on the sample. And also for the other transformation, they depend on the class label. But there must be a way to map from this pipeline into a CNN. Well, I can probably open up for questions if there is time.
Thank you very much. A quick burning question? Yes.
Quick question. To use Norbert videos for sports to do the recognition, have you considered looking into depth information by having
so when we started that, we thought, wow, it's going to be too easy if we use that. But actually, no. The main reason is that we wanted to work on archive data. So we have, and also, actually, before going to depth data, the question was actually, why don't you use HD data, right? This is all SD. Because essentially, if you look at tennis data, I mean, if you want to do anything significant with those tennis data sets, you need to go back way, before HD broadcast even started. Yeah, but obviously, if you give more information, you get better results.
The whole pipeline is kind of independent. What you do in terms of the features.
Yeah, you just need to do a little bit of adaptation to these steps. Yeah.
Great. Yeah. So
I was wondering if there is some relation between the transfer learning from a data set to another one and continuous learning of a certain task. Like if you have a task that you learned on a data set, and then you want to continue to learn in time and to improve your algorithm?
I think this would have a longer
I
answer.
think this is a good question to mark for the afternoon session. We want to
Yeah.
kind of have a panel discussion.
Yeah.
It is intentional that kind of you will find that the morning talks might be more quite mathematical. So hopefully everyone is awake. And now allow me to